Okay, so this question was about refractive index, and it might look very similar to a question that you guys have done, but actually we changed some of the values around a little bit to make it a different style of question. So it says predict and give a reason whether the reflected ray of Y, so we're looking at this wave here, undergoes a phase change. So in this case, it's going less dense to more dense to less dense. So the reflection taking place is here, where it's on a more dense to less dense boundary. So no, there's going to be no phase change because it's reflecting off a lower refractive index medium. Remember, if we're going off a lower refractive index, we get no phase change. If we're going off a higher refractive index, then we do get a phase change. Okay. The next question then said, what is the path difference? If this is here, this is D, it goes there and it goes back. So its path difference is just simply 2D. Remember, the angles are so small here, we ignore them. So it's a 2D path difference. It then says calculate the smallest value of D that will result in destructive interference between X and ray Y. Now, because we're doing less dense to more dense to less dense, so less to more to less, we could use the 2dn is equal to m lambda for our destructive interference equation. Simply then plug in the values and you get all the way through. Again, when it's at the smallest, we're using n is going to be equal to 1. I apologise, I wrote 4 earlier because I was doing the previous question where n was 4. But for this one, it's the smallest one, so m is going to be equal to 1. And that should give you 2.12 times 10 to the minus 7 metres, or 212 nanometres for your question. Then says, discuss a practical advantage of this arrangement. Essentially, at one wavelength, or a particular wavelength, okay, maybe it's wavelength of light that we're dealing with, the reflection off the front of the lens, okay, or the glare is being reduced. We want to have that destructive interference. Okay, if we have the lens coming off and we get destructive interference taking place, we're going to get less reflection happening back. But remember, this is specifically for a certain lambda, so at one wavelength or at a particular wavelength, the reflection of the front of the lens, the glare is being reduced. The next one then was a little bit about single slit interference. Light from a point source is incident on the pupil of the eye of an observer. Okay, we're looking at an eye. Okay, we're looking at circular. Okay, it says draw on the axis the variation of the angle of the intensity on the retina. Essentially, a single slit drawing needed to be done. So I drew a high, big central maxima, and then subsequent minima that were much smaller. I said drawing them to be much smaller. In the guidance of the mark scheme, it said it needs to be at least a fifth. You just want to make sure you keep it really, really small. Okay, as small as possible. They shouldn't be coming up to halfway, a quarter. They should be really low on there. So about this, they actually for this one haven't even stated that you needed to draw this to be the same thickness as this, but it is something to bear in mind on other mark schemes. That may come up, and the central maxima is double of the first minima. It's not on this mark scheme. You got one mark for the pattern, a second mark for the height, in this case what they were looking for. And then the last part was estimating in radians. I've written meters there, I should have written radians. The smallest angular separation, the two distinct sources. So again, we're just using our lambda, 1.22 lambda over b, 1.22, 656 nanometers. Okay, divided by, again, my b, it was over back here, 2.8 millimeters, so 2.8 times 10 to the minus 3. Plug it all into your calculator and you get 2.9 times 10 to the minus 4 radians for your theta coming through.